Welcome back. We have looked at linear systems graphically, but graphical solutions aren't always convenient. Sometimes we would like to simply work algebraically, and so let's explore two different methods for doing that, both the elimination method and the substitution method. Both are tools in your toolbox. They could be, you could choose the one that you like in a lot of situations, but I often find that the solution I like the most is chosen for me by the problem type. So it's excellent to be fluent in both of these types of approaches to these problems. For elimination-based solutions, we're going to take advantage of the fact that we can add equations together to eliminate variables and shake things up. So here, similarly to inverse operations, where if I add the same thing to both sides of the equation, that's permitted. If I have two elephants on one side of a scale and two elephants on the other side of the scale, that will be balanced. And then if I add two people to each side of the scale would still be balanced. If I remove one elephant from each side of the scale, it would still be balanced. And because these are equations where I am told that negative x plus 3y is always equal to 6, I could add 6 to one side of the equation and add negative x plus 3y to the other side of the equation, and it would be the same thing as adding two people to both sides of a scale or removing one elephant from both sides of a scale. It would still be balanced. So that's why this strategy is permissible. That's why it's allowed. In this case, I notice that elimination is very convenient. If I choose to add this equation to that equation, it will eliminate the variable y because 3y minus 3y is 0. So let's add these together. Negative x plus negative 10x. Negative 1 plus negative 10 will give me negative 11 of that thing. So this is going to give me negative 11x plus 0 from 3y minus 3y will equal 33. 6 plus 27. Now I have the line negative 11x is equal to 33. So I can divide both sides of this equation by negative 11 to find that x is equal to negative 3. This is half of my solution. I now go back and I can choose either equation 1 or equation 2 to substitute this x back in, and I'm going to choose equation number 1 because it's just a little bit simpler. So there I would have, now I'm going to go over here. I know that negative 3, this is substituting in for x, plus 3y is equal to 6. Negative 3 is 3. 3 plus 3y is equal to 6. Subtracting 3 from both sides of the equation gives me 3y equals 3. And then dividing both sides by 3 gives me y equals 1. This is the other half of my solution. So now I'm ready to input this as negative 3, 1. Submit the answer. So this is elimination. We add the equations together to get an equation with one unknown, one equation. If your numbers of unknowns outnumbers the number of equations you have, you cannot solve this. You will have a relation. There will be an infinite number of x's and y's that could solve that. But once we have one equation, one unknown, two equations, two unknowns, or three equations, three unknowns, these are solvable situations. And we can use elimination and substitution to get ourselves to this type of situation where we've solved for one of the variables. And then we can move forward and find the unique solution to that system. Now let's take a look at a more challenging elimination example. So here we have, and this one is not that much more challenging. Let's take a look and see if we can find this is better. All right, so now I have these equations that I'm working with. They are 4x plus 3y equals negative 5. So let's copy that down. 4x plus 3y equals negative 5. And negative 5x minus 9y equals 22. In this case, I can't simply add one of the equations to the other equation to eliminate a variable because none of my coefficients are lining up and have an equal value. But I can create that if I call this equation 1 and this equation 2, and then I create a third equation, which is I take equation number 1 and multiply it by 3. So I'm just going to take this equation and multiply everything by 3. I've noticed that then I'll have 9y, and that would cancel away this negative 9y. And that would be very convenient. However, maybe I want to do it the harder way to show you how to do the harder way. Let's say I want to eliminate x here for some reason. I'm only interested in solving for y, so I just want to eliminate x and solve for y. In that case, I could take this equation number 1 and multiply it by 5. Take equation number 2 and multiply it by 4 to create 2 new equations. Let's take a look at how that would work and why I know that I can do that. Hey, zoom in for me, will you? There we go. So 4x plus 3y equals negative 5. I'm going to multiply this whole equation by 5 to create a new equation. 20x, that's 4x times 5, plus 15y equals negative 25. And then equation 2 multiplied by 4, I'll put underneath. Negative 5x times 4 will give me negative 20x. Minus 9y times 4 will give me minus 36y equals, in this case 22, 88. Now I can add these two equations together to eliminate x. I have a new equation 3 and 4, and I'm going to add them together. I always choose adding together my equations, but some people will subtract equations from one another. That's totally fine. Avoid sign errors. Make sure you're very careful with your signs. 20x plus negative 20x gives me 0, so I'm not going to write down anything. 15y plus negative 36y will give me 21y, but it's negative. And that's going to be equal to negative 25 plus 88, which will give me 63. So looking at this, I can tell y is negative 3, because when I divide by negative 21, both sides, 63 divided by negative 21 is negative 3. So I have y is equal to negative 3. There's half of my solution. Now I can go back and substitute into one of my original equations to find the other half of the solution. I'm not going to write that out. I'm going to do it in my head. So I'm going to put negative 3 in there. I have 4x minus 9 is equal to minus 5. Add 9 to both sides. X is 1. So you can solve these on your own using your inverse operations. 1, negative 3. That's how you can use an elimination strategy to solve systems of equations. Any questions? Absolutely hit me up by email or on the D2L, or come chat with me at lunch or anytime you choose to.